Okay, so I think we're on. And remember at the start, at the end of last class, I mentioned about Eureka and how I was talking about genetic programming and how we could generate these expressions that were like a tree, and then we would lop branches off the successful trees, and they would mate, and there would be little mutations, and we would do this a gazillion times, and ultimately pretty good formulas would emerge. And this is another way of doing a universal function generator, which is a key piece of machine learning. And I mentioned that one of the pieces of software that's used for this is called Eureka, which I have now managed to download. And apparently, if you're not an academic, it either costs $12,500 or $2,500, but I showed them my little academic ID card and it was free. So, and I think you guys can do the same if you want to play with this. Anyway, the idea here is that we've got, I think about 100, 200 pieces of data, whatever it is, 100 pieces of data, and we just have 3 variables. So this is almost a toy problem. This is a very easy problem. So there's our data. We get to prepare our data, which is, you can do things like normalize it so that it all has a standard deviation of 1. And I guess I did this here, and I don't quite know how to undo it, so we'll just leave it. And then you can tell it, look, this is what I want. I want to predict y as a function of x and w. Here are the primitives that I'm going to permit it to use. I'm going to permit it to use a constant, a variable, addition, subtraction, multiplication, sines, cosines. I don't see why it couldn't use negation. Maybe it's locked in. And there are various other things, and these are sort of the point scores, okay? If you use a sine function, that costs you 3 points. And if you use a hyperbolic, well, I guess we didn't put that in there, a hyperbolic tangent, that would cost us 4. So here's what we're permitting ourselves to use. It's actually cheating, isn't it? Because it knows those are good ones. And let's see, stop. And let's start running the search. And what we should see, resume from previous search, no, let's start from scratch, is, okay, it's starting to generate, you probably can't read it, but it's starting to generate lots of expressions down here. And it is calculating fits. And you can see now how it's doing. It is improving its fit as time goes on, as it's evolving. You can also see that, I like this curve a lot. This shows the trade-off between the error rate and the complexity of the expression. And by selecting, this is sort of showing, okay, if you want a really good fit, this is the best one it's found. This is what, and you can see it's kind of wiggling around. Whereas if you're more mellow about it, you want something simpler, okay? This is much simpler. That's why it's here on the trade-off between complexity and error, and it's sort of kind of tracking the data, okay? And here's another one, okay? And so the idea is that you let this run for a while until you're tired. How many of this has it done? It has run, and it's or it says it's validating. I don't know exactly how it's doing it. It used to tell you like how many evaluations it had done. Not yet. All right, let it run a little longer. This is a great way to spend an afternoon, is to watch Eureka do things. And, all right, I'm bored. So we will, how do we get it to pause? Let's get it to pause. Oh, here it is. Okay, so it has run 16,000 generations of evolution, and it's done 2.2 billion formula evaluations at a rate of 19 million a second. And I guess it goes through 147 generations per second. So isn't this, I mean, it's just sort of simulating long scale evolution. And now what you can do is you can have it run various reports. So I have no idea what they've done to this. But the idea is, look, here are some possible solutions. Here's one that's pretty complicated. where it's got nested sign expressions, but it's showing you that it actually gets a pretty good fit. Whereas if we work our way down, here's one that's really, here's like here's a line, okay? And the virtue of a line is it's very simple. The problem with the line is it doesn't really explain the data. Though, like something like this, it depends what you need it for. That might be okay, and that's a relatively simple expression. So this is one of the forms of machine learning, is this idea of basically genetic programming. This was invented by a guy named John Koza, Koza, in like the 1980s, and it might not have been that practicable then because computers weren't that fast, and if you wanted a fast one, it was very complicated, but now it's evolved to where you can do whatever we just did, 2 billion evaluations on our data. Yeah.
Does it define the constants?
Yes, it is putting in a constant. It's like here. I guess this model minus d. So there's its constant term.
Okay.
And so it is both coming up with a functional form, this messy sign thing, and coming up with coefficients that fit it. Okay? And there is sort of a dark art to doing all of this. Like, do you simply evolve the functional form and then do a regression to generate the coefficients? Or do you really let the coefficients evolve and have some rule for how coefficients mate? And the other package that does this I mentioned is Data Modeler, which is a Mathematica package, and there are at least 500 options to Data Modeler of how you can control very finely. And the reason they can charge $2,500 or $12,500 for this product is, and this is where the people got started with it, if you're running a large chemical plant and this is 30 variables that affect the success that you have in refining gasoline, this is nothing, right? And so if you can discover how these complicated systems actually work, that you can't really come up with a theoretical model of it, but if you can come up with a good emulation, that works pretty well. Let me just add, since I'm here, that the other thing that one can do, which works very well, is, let's say we get 3 or 4 pretty good models here, right? One of the things you can do is look for models that are both good and a little bit diverse in that their predictions are slightly different, and then have those models either vote or take like the median of the predictions of those models, and that sort of ensemble modeling is sort of another level of meta modeling where you're putting the models together. And this is whatever I was going to say, which I've now forgotten. Okay, so yeah.
Can this also kind of show you points that you want to take out, like if you scroll up?
Yeah, sure. So let's look. For example, this point here seems to be problematic. It's pretty far from the fit, and if I use, say, this model, why these points are troublesome. And so if you simply if your goal was not to come up with a good function, but to simply show fit, this will give you a clue as to what points it would be helpful to eliminate. Okay, so you can use that for good or for evil, but it will identify for you the residuals that are way out there. Okay, and apparently you can run this in the cloud and buy cores at 31 cents per core hour. So this is, pretty obviously a product that is designed to make money, right? Which is nothing wrong with that at all. All right, so that's Eureka. And if you log on to their website, which is Newtonian.com, Newtonian, I don't need to say this. It will, I think you can do the same thing. Do you have like picture IDs for UH?
Yeah.
You like take a little picture of your ID. All right. Okay, so let's go back though to other methods of machine learning, and there are a couple that I want to talk about. I guess the first thing I want to do is to talk about doing it in Mathematica and seeing the diversity of techniques that are available. And one of the things I learned this morning is that you really need to make this bigger, both for you and for the screen recording, assuming that it's actually doing anything. All right, so what I want to do here is to show you how to do machine learning in Mathematica and how successful it is or isn't. All right, so I'm going to create a function. There's actually no noise in this function. It's just a slightly complicated polynomial function. And you don't really have to understand what it is. All you need to realize is that this, remember the CDF function of a distribution produces values between 0 and 1. It's saying how much of the distribution lies below a certain point. And so if we round the result, we're always going to get either a 0 or a 1. So I've built a little classifier here. And, you know, in a perfect world, the system would pop up and say, this is your system. It would say, that's the formula that you're using. But our machine learning techniques that we have here aren't going to do that. They're going to build systems that emulate the result of this classifier. Okay? So let's start with a clean kernel. All right, and I'm going to seed my random number generator. By the way, I think this is up on the class website, so you can play along. I'm going to seed my random number generator so that I know what's going on. I'm going to create 100 random points of xy values between -10 and 10. And I'm then going to put them in a form that our machine learning algorithm likes. I'm going to take for each point, I'm going to create a rule that takes it from itself to the result of the function applied to itself. That's what this mapping, and this is one of those anonymous functions in Mathematica. So I do this, and this is what I get. So this point maps to a value of 1, and this point maps to a value of 0, and this point maps to a value of 1, etc. Okay? And we can now look at the result. What I'm going to do is first I'm going to select points whose value is 0. And now I'm going to select points whose value is 1. And I'm going to plot those, and Mathematica is smart enough to realize, oh, you probably want to color those points differently. And so we'll just generate a plot. All right? So there's a plot. That's the pattern. That's what that function actually produced. And now the question is, can we emulate that? So what I want to do is to create some testing and training and testing points. This is a sort of we talked a lot about cross-validation in the last class, and this is kind of a cheap and dirty way of doing validation. What you basically do is you split your data up, and what proportions go where. There's an art to it. Some people say 50-50, some people say use about 2/3 for training and 1/3 for testing. Usually not too much turns on precisely how you cut it up. The central point is, though, that you want to reserve some data that your classifier's never seen so that we can see how will the classifier perform when it encounters new situations. Right? So here I decided I'm just going to split it in half. Right? And this is now the index to the points that I'm going to take. My training data is going to be point 100 and point 40 and point 99 and point 12 and point 80, etc. And my testing data is just everything else. The complement operator is like a set complement, which you might remember from some time or other, where you're just saying, it's like subtraction with sets. Here's the big set, here's what you already have, and complement says what's left over. Okay? So that's what testing does. And so now we can take a look at what are the training points. Okay? So this is...
Professor, if it's taking the complement, you shouldn't have the same data point in both.
That's correct.
So 11 is the second to last one in training, and 11 is listed there in testing.
You have just caused trouble. You're absolutely right.
And then 83 also.
Okay, so what does this mean? This means there's a bug, and I'm not seeing what the bug is. All right, let's look at this. What's the size of training? That's correct. What's the size of testing? That's weird. How long is our data? Okay, so this can't be. Let's take this apart. That's 1 to 100. If I take the complement of this with training, okay, anyone have a theory what's going on? This is yet another reason not to record class. Let's look up the documentation for complement. I thought I knew what it was. Gives the elements in E all which are not in any of the EI. So this is 100. It's got to be something stupid. Are my brackets correct? Let's do it again. Let's see if the problem. Could I be out of sync? I bet I'm out of sync. Okay, I got a theory. I have a theory. Let's try this theory. Let's start again. Let's seed random. Let's run that. Come on, evaluate the cells. Okay, now let's see if you at least see any overlap. All right, well, let's try this. There's an intersection command in Mathematica, and this should be the null set if I've done this right. Okay, so I believe what happened is they simply got out of sync with each other, and I was using an old training, because I don't see anything wrong with the code. All right, good. We are over that little hurdle. Actually, this would be a good test. Is the length of testing 50? No! How can that be? What's the length of training? Got it. I got it. I got it. Random choice permits duplication.
Yeah, there's two 99s there.
Why didn't you tell me that?
I just saw it.
All right. We're in business. Okay. The only thing that's going to happen is now I have different random numbers than I did before, but really it doesn't make any difference. This thing should work. All right. So this is what we've got to figure out. We've got to figure out what function could generate these points. All right. So here are the classification algorithms that were available as of Mathematica 10.0. There's a new one that's added in Mathematica 10.01 if you have downloaded it yet, which is neural networks. And this morning I discovered a bug in Mathematica 10.01, which is this stuff here, which you don't really need to worry about. It is to compensate for a bug. This you haven't seen before. This is just a way of getting Mathematica to print stuff out as it's doing things, okay? So this is the function that we're going to use. It's a somewhat complicated function, but it's basically going to produce a report. It's called process. We're going to take our data. We're going to take our indices into the training set, our indices into the testing set, the method that we want to use, as well as any other options that we want to pass to classify. That is, classify, like lots of Mathematica functions, takes all sorts of options where you can fine-tune it, and this is simply a way of passing it. So what are we going to do? We're going to do our classification on the training data using the method as well as any options that we've passed. We're then going to measure how we did using our classifier C on the testing data. We're going to look at its accuracy, and we'll make a little confusion matrix plot. What we're then going to do is we're going to get all the information we can on our classifier. That's what this is doing. It's saying, look, take all the properties of your classifier and now tell me what they are. We're then going to make a three-dimensional plot. Okay, and the three-dimensional plot is going to tell us what probabilities the classifier assigns to the value of a point being 1. Okay, so it's looking for oneness here. And so if it's really confident that it's going to be a 1, we're going to have the value of our plot, the height of our plot will be 1. If it's pretty confident it's a 0, the height of our plot will be 0. We're also going to build a region plot, which I'll show you. I'm not sure we've seen those before, showing where it thinks the value of the function is 1. And in this final piece of code, we're going to compare what our predictor is saying with what the actual function is. That is what a perfect emulator would see. Okay, so this is the code, and I acknowledge it's a little more complicated than stuff that you've seen, and I also realize it's going to work much better if I evaluate LP, or zeta, I'm sorry, that's zeta. All right, and so now let's start using it. We'll start with one of the simplest classifiers, which is naive Bayes, and I'm going to, in the second part of class, I'm going to show you how naive Bayes works, but it basically uses Bayes' rule in a naive way, which is how it got its name, right? So let's run it. And I'll tell you, the virtue of naive Bayes is it seldom does really badly, and it's always really fast. So if you've got a lot of data and you don't need something brilliant, naive Bayes is a pretty good way to go. All right. So here's our confusion matrix. The actual things are here, and you can see that most of the action is on the diagonals. 40 of our things are correctly classified. 8 aren't. Here's the surface that it's predicting. Here's its sort of confidence level. And if you look at this, if you sort of tilt, actually we can tilt it. If you kind of tilt it on its side there, you can see, if you use your imagination a little bit, that it actually, we haven't seen what the function actually looks like. All right, so this is exactly the same thing. This is, instead of using probabilities, this is saying where does it think it's 1. And in this final graphic, you can see how the naive Bayes classifier, which is blue, matches up with the orange classifier, which is the actual function. Okay? This is, if you did a perfect job, you would get orange. And what our naive Bayes classifier has done is to produce blue. And the fact that it has sort of rectangular pieces is not a coincidence. Naive Bayes produce rectangular systems. And you can kind of see why it did what it did. That is, it didn't confront a lot of points over here. And so it didn't know how to, it doesn't know that it should be doing something different as a result. Okay? So, support vector machines. Okay? Let's see how they, but what was the accuracy of our naive Bayes? 80%. Okay? Support vector machines. So let's run that. Let's see how it does today. Okay, so it's getting 90% right. I mean, as far as machine learning goes, this is an easy problem. Okay? If we ran this enough, I could do pretty darn well with this. And you can see that the support vector machine is taking a longer period of time. What you can see here, see how it says kernel type radial basis function? What that is telling you is it is actually using a method similar to the one I described in the last class, where to move, remember that it's sometimes hard to find a separating line or separating hyperplane if you're confined to two-dimensional space, if you're confined to the space in which the data actually exists. It's hard to draw a line that will actually perfectly separate this data. But if I could move my data into a higher dimensional space, then it turns out that there's always a separating hyperplane. In fact, there may be multiple separating hyperplanes, and the job of the support vector machine is to find the best one. So, remember I mentioned that the one way to take your data into a higher dimensional space is, instead of using the XY coordinates, to use its distance from every point that exists. Okay? And since there are 50 points, that will move it into a 50-dimensional space. And once you're in the 50-dimensional space, you slice it up, and then you project it all back down. And some of this other stuff, this support vector machines are complicated as to how you actually do it. But here's what it thinks the system's going to look like. And that kind of looks right? So here's what it looks like when I put this in 2 dimensions. And so it's got the idea. It's figured out how this works. So for this kind of a classification problem, we'll see how it does on these new numbers. My recollection is last time I did this support vector machines, and neural nets, somewhat to my surprise, did the best on this kind of problem. And this is one of the things is, these methods, they may work well on one problem and not so well on another problem, and there's no real way to tell that I know of as to which method is going to work best. You kind of have to poke around and try them. Oh, look at this. Let's see how nearest neighbors does. 90% also, okay? And it has the virtue of being very fast, and it has the virtue of not printing out.